welcome to our 28th session. In this session, which I believe will be the last session, that will be talking about the bipolar junction transistor. And next time we're going to flip over to the right side of the device structure tree. We'll be tying up some loose ends. We'll be spending a fair amount of time on that. And then we'll be continuing with the second order effects. Last time we looked at the second order effects, which are detrimental to device performance. Today we'll be looking at the second order effects, which we can do to make better devices, and perhaps not even second order effects. The heterojunction bipolar transistor is a whole new device. And if we have time at the end, we'll be looking at one or two examples. But first, let's turn the clock back to the 1910, 1920 time frame. The movie is called Soul Keeper. It tells the story of the relationship of Carl Jung to Sabina Sperline, and this is a clip which occurs in a mental institution, probably someplace in Austria, and shows the power of music. The director of the institute is not very happy that the people are enjoying music. And let's see what happens, and we'll be back in about 2.5 minutes.
Silence! Silence! You see what your patient is up to, Dr. Jung? Tell her to stop!
Just be right, please.
With pleasure, Dr. Jung.
I'm going to be discharged today, after being in hospital for almost a year. I've started eating regularly, and even having periods again. Dr. Jung said it would be enough if I see him twice a week from now on.
Welcome back. This is a list of some of the topics we'll be covering in today's session. We'll be spending a fair amount of time in tying up some loose ends. This is our last attempt to clarify some of the aspects of the bipolar junction transistor. We'll be looking at terminal currents. We'll be perhaps not saying clearing up, clarifying some aspects of the early effect. Then we'll be looking at saturation forward active modes from a little bit different perspective. This should be very short. In fact, both of these should be fairly short. And then we'll be taking a look at the reverse active mode from, again, a little bit different perspective. Then we'll be looking at some of the things we can do to enhance the performance of a BJT, specifically non-uniform base doping. Excuse me. The more important is the HBT, or the heterojunction bipolar junction transistor. And finally, we'll be ending our session with a video clip. Okay, so first, let's, in the tying up some loose ends, look at the terminal currents. We've seen this picture before. Notice that there is no actual current as a function of position. This is the IEP, is the total current which appears at the emitter base junction, and the ICP is the total current that appears at the base collector junction. Both currents are composed of two components: holes injected from the emitter to the base and holes injected from the collector to the base. So we add up those two components at x prime equals 0, and then we add them up at x prime equals WB at the end of the base. And here are those two expressions. And first we'll ask the question, what are the units of the right side? We know the units on the left side are the units of current, which are coulombs per second, or amps. Now, if you look at the right side, it should be clear by now that everything in this bracket is unitless. And the reason is, for the exponent here, we have energy divided by energy. Energies cancel out. Here we have distance divided by distance. That cancels out. Same thing in the second term. So everything here is unitless. And we're hoping that the units of this term right here, the coefficient, will be units of current. And we do that. Of course, Q is in coulombs. The diffusion constant is in centimeters squared per second. The units of area are centimeter squared. The units of distance, centimeter. And the units of excess carrier concentration are centimeters to the minus 3. So we have centimeters fourth divided by centimeters to the fourth on the bottom. Centimeters to cancel out. And we have left with coulombs per second, which are the units of current. So indeed, the units do conform, and the right side is current as well as the left side. So the first case that we consider is the forward active mode, where we have forward bias here and reverse bias at the base collector. So if we have forward bias here, this is a big number, much greater than 1. 1 goes away. If we have reverse bias here, this is a relatively large negative number, so this term goes to 0, and of course we have minus 1 times minus 1, which gives us a plus 1. Do the same thing for the ICP, and we get two terms. These are general terms for the terminal currents with forward active mode. And of course, this is the general case. So first we consider the long base case, where the width of the base, neutral base region, is much greater than the diffusion length in the base. And therefore, well, we have to look what happens when this term is very large, and what happens when this term is very large. Well, I'm going to claim that the whole thing reduces to the coefficient multiplied by Q to the E to the Q, VEB divided by KT, and the reason is that the hyperbolic cosh divided by the hyperbolic sinh, which is identically equal to the hyperbolic, or definition of the hyperbolic cotangent, goes to 1 as x goes to 0. And the hyperbolic sine goes to 0 as x goes to, as I say, x goes to 0, as x goes to infinity. And the hyperbolic sine goes to 0 as x goes to infinity. So this term goes 0, this term goes to 1, and basically that's what we have. And for the ICP, this term goes to 0, and this term goes to 1. So for the ICP, we have this term right here, and because ICP has been defined as going from right to left in the negative direction, this term is actually positive, and that makes sense because we know that in the forward active mode, the effect of the collector is to make the total current IC greater than it would have been without the effect of the collector. So that makes good sense. Okay, so let's go back here. Let's see, what do we have? Okay. Now we do the small base. This is the opposite, or the inverse of the large base. The small base, the base width WB, is much less than the diffusion length. And in that case, we have the IEP collapsing to this term right here, and the ICP collapses to this term right here. Let's see why that is the case. For very small values of WB, the cosh goes to 1, and the cinch goes to WB over LB. So that gets flipped over here, and the same thing over here. The cinch of the expression WB over LB goes to WB over LB in the denominator, and it flips, and that's what we have for IEP. And for ICP, we do exactly the same thing, and we get the same result. IEP equals to ICP, and that is exactly, well, oh, there's one other thing I should tell. The minus sign flips to being a positive because ICP, just like the previous case, ICP is assumed to be in the negative direction. So if we have a minus sign, it becomes positive. So IEP is precisely equal to ICP. I perhaps should say that the opposite way. ICP is precisely equal to IP. What comes out is exactly the same as what comes in, and that is exactly what we would expect because there is no recombination, so we lose no charge in the base, and the output is equal to the input. So the reverse active mode, it is exactly the same. I feel it would be a little bit redundant to go through that. The results are identical. Now the ICP is replaced by IP, IEP, and everything is just reversed. And for example, for the small base approximation, what comes in here comes out here. So everything is exactly reversed. And the last case is the saturation mode. And the saturation mode, the currents are equal and opposite. Both junctions are forward biased, and they are equally forward biased. And let's see, where is it? Oh, it must be here someplace. Okay, there it is. And I'm going to call that forward bias Misabe applied bias because they are precisely equal. So now I write the general expression with equal biases at the emitter base junction and at the base collector junction, and this is what we have here. So IEP is precisely equal to ICP, but the minus sign stays the same. And what is the magnitude of IEP, I should say, is equal to the magnitude of ICP, but they are equal and opposite, and therefore the total current is precisely 0, and that is exactly what we would have expected in the saturation mode. Our next topic is going back to the early voltage. So I've labeled this clearing up the early voltage. So what I've done here is taken this picture, what we've seen before in the last session, and I've color-coded it. The two red lines represent small IB, and that's small forward bias at the emitter base junction, and the two blue lines represent larger forward bias at the emitter base junction. Now, the difference between the two blue lines is that this line, line 3, represents a small reverse bias, and line 4 represents a higher reverse bias. And you can see that line 4 has a much bigger slope than line 3, and line 2 has a bigger slope than line 1. Furthermore, the difference between the slopes of 3 and 4 is larger than the difference between the slopes of 1 and 2. It's almost like the slope of the slope. In mathematics, we call that the second derivative. So if we look at the output current voltage characteristics, we see that point 1 represents this line right here, and then point 2, because it has a higher slope, it has a higher current. And the same thing for points 3 and points 4. And if we project those two lines, supposedly they come to a common point called the early voltage. Now, one point I want to mention here, which I probably should have done previously. There's also a depletion region here at the emitter base junction. We don't show that. And in fact, the depletion region at the emitter base junction can be comparable to the depletion region at the base collector junction. However, when we put a forward bias on this junction, the depletion region decreases, and it doesn't decrease very much. It gets narrower, but only slightly. And the reason is small IB would say 0.6 volts forward bias. The large IB point up here would be 0.8 volts. That's only 0.2 volts difference between here and here, 200 millivolts. Whereas the difference between a small reverse bias would be, say, a volt, and a high reverse bias would be, say, 10 or 20 volts. That's a big difference. So we see that this widening of the base collector depletion region at the base is much greater than the narrowing of the depletion region at the emitter base junction. So that's why I don't include that here. This is the important part right here. Now, the question is, why do the projection of these lines always meet at a common point? It doesn't really make all that much sense, or it's not intuitive that that should in fact be the case. And I tried to prove that starting with the premise that the proof was going to fail and that these points would not meet at one common point. One would be a little bit over here and the other would be a little bit on the left side, and we can say, well, they're sort of close. It works out that they do meet exactly at the same point, and I've shown a link here where you can see that proof. It would take a little bit too much time to go through that, but it's a very nice proof, and this is from India Institute of Technology, which is a marvelous school. So check that out, and you'll see that they do indeed prove that the lines coalesce to one single point. Okay, so the next topic in this potpourri of topics is saturation forward active mode. This is the saturation mode here, and this is the forward active mode. This is what we would like. This is what we want, but this is what we get. And I just want to give a kind of sloppy proof that indeed we always get the saturation mode. We can never get the ideal case here. And if we look, this is for an NPN because it's VCE, so if we write an explicit expression for VCE, we have it's equal to VBE plus VCB. This means that the collector is positive with respect to the emitter, the base is positive with respect to the emitter, the collector is positive with respect to the base. Okay, so for an NPN, this region here is very small VCE, approximately equal to, more or less equal to 0. So if I put a forward bias of 0.6 volts, which means that the base is positive with respect to the emitter, and for an NPN, that's exactly what we want, because we want to push electrons into the base emitter junction, to narrow the junction, and then because VCE is approximately 0, it means that VCB must be minus 0.6 volts, which means that the collector is negative with respect to the base, which means that the base collector junction is also forward biased. So if both junctions are forward biased, I get very little current, and that is exactly what we expect in the saturation mode. In order to go to the forward active mode, I have to increase VCE to approximately 2 volts, and then keeping VBE constant at 0.6 means that VCB will be 1.4, and that is enough to go into the forward active mode. So the point is here that saturation always exists when the two modes or the two junctions are forward biased, and I can't get around it. It's always there. One more look, and hopefully the last, at the reverse active mode. So this is the standard case for PNP structure. We have current 1, which is the big guy, holes emitted from the, or ejected from the emitter to the base, and 3 is the little guy, holes ejected from the collector to the base. So we have a standard doping 10 to the 19th, 10 to the 17th, 10 to the 15th. But suppose the fabrication engineer, ouch, that could be me, makes a mistake and reverses the doping density. So now we have lightly and we have heavily, or degenerate, with the same thing, 10 to the 17th in the middle. Well, the boosts, as I've tried to explain here, are exactly the same. So the whole currents pretty much haven't changed, because the boost here for, say, 0.6, I have a 10 to the 10th boost for the holes, and I have a 10 to the 10th boost for the holes from the collector to the base. However, it's current component number 2 which has changed. These are electrons which are boosted from the base into the emitter. Now, because the emitter is now lightly doped, that boost is not 10 to the 11th, which it was before. 10 to the 11th is when we had a degenerately doping here, 10 to the 10th times 10 is 10 to the 11th. It is now, because I have 10 to the 15th doping here, it is 10 to the 5 times 10 to the 10th, or 10 to the 15th, which is 100 times the whole boost. The whole boost was 10 to the 13th. Now the electron boost is 10 to the 15th. So the beta, instead of being 100, is 0.01. However, there's a way out. It's not totally lost. If I put a reverse bias at this junction and a forward bias at this junction, I reproduce the beta of 100. And that's kind of an interesting thing. So the takeaway is that doping density really matters, and you want to make sure that the doping densities are right. Now we finish this potpourri of review, and let's get on to the new stuff now. Non-uniform base doping. So to look at non-uniform base doping, I'd like to go back to the hot plate experiment. And remember, we put a silicon sample, could be N-type or P-type. It has to be doped, and we put it between two temperatures. Hot plate, maybe 300 to 400 degrees C, and then the other is supported more or less at room temperature. And we will measure a voltage between these two. Now, if we look at this sample, we ask, is it in equilibrium? And the answer is a resounding maybe. It is in material equilibrium because there's no external circuit. So there is no charge that can flow around the circuit. The DVM, the digital voltmeter, that's what it stands for, has a really high resistance. So this does not represent a circuit. So there is no charge that can flow between the two left and the right edges. However, it is in non-thermal equilibrium because there's a hot side and there is a cooler side. So there is a temperature transfer, or there's a heat transfer, not temperature. There is a heat transfer between the hot to the cold. The energy band diagram, I hope you recall this, looks like this. The hot side is closer to intrinsic, whereas the cold side has the full, say, weight of the doping. In this case, it is N doping because the Fermi level is close to the conduction band. All of the band edges are tilted, but the Fermi level representing the fact that we have a material equilibrium is straight and horizontal. Okay. And we also said that if we were to put a circuit, connect a wire here, connect a wire here, and we draw a circuit around there, hopefully putting in a little resistor, we will indeed get a current. And the reason is because there is an external energy source, namely the hot plate. If we turn off the hot plate, we have this circuit and current. We have a current, and we can do work. We can lift a weight or something like that. However, if we disconnect the hot plate, eventually the current will go to zero because we come into thermal equilibrium. So now we ask the question, this is the next stage, is it possible to produce exactly the same energy band diagram without the hot plate in another way? And the answer is yes. Rather than varying the temperature across the sample, we can vary the doping with position. And if we look at this, we have a heavily doped left side and a lightly doped right side. The energy bands all bend from left to right. They bend up, and the electric field is from left to right in the positive direction. We also have a diffusion current, which goes in the opposite. The drift current will be in the positive direction. The diffusion current will be in the negative direction because electrons will be going from left to right, which represents diffusion going from right to left. So we have not only thermal equilibrium, we have, again, material equilibrium. And that's all I'm basically saying here. The interesting thing about this particular case is that if I connect an external circuit, connect a wire from here to here with a resistor or some kind of load that work that I want to do, I will get nothing. No current, no work, no nothing. Unlike this case, hot and cold, where I can get work out of this. And the reason is that this is purely internal. However, and this is the whole idea of non-uniform base doping, should an electron find itself, or not an electron, hole, find itself right here, right at this point, it's going to feel an electric force. It's going to be pushed by that electric force. It's going to go faster. There will be a drift component. So if I have this as the base region in a PNP type structure, and I have holes coming in from the emitter, which is over here, they're going to find themselves in a region where they feel an electric field. So not only is there going to be a diffusion component, there's going to be a relatively healthy drift component, which will accelerate them, and that will improve the device performance of a bipolar junction transistor. So non-uniform base doping gives an electric field, which gives an electric push, which gives a healthy drift component to charges which find themselves in the base, and that gives an increase in the current and an increase in the device performance. Okay, the last topic that we're going to be looking at today is the HBT, or the heterojunction bipolar junction transistor, as compared to what we've been studying until now, which is the homojunction bipolar junction transistor. Hetero means different, homo means the same. So what we're going to do here is we're going to create a structure which has different materials, specifically different materials in the emitter than we have in the base. So we can have a different material in the emitter as compared to the base and collector, or we can have a different material in the base as compared to the emitter and the collector. The first one we'll be looking at is we're going to put a different material in the base and keep the materials in the emitter and collector the same. So the idea is here we're going to try to enhance the performance by creating a quasi one-way gate. And you recall that for the normal device, the homojunction BJT, if we put 6 volts bias on the emitter base junction, we have a boost of 10 to the 10th, and that boost is for PNP, or holes injected into the emitter, and for electrons injected from the base into them, I should say, for holes injected from the emitter into the base, as it is for electrons injected from the base into the emitter. We're going to change that ratio, and that's the whole secret here. And that's what creates the enhanced performance. So let's see how that works. So let's take a look at the part of the periodic table, column 3, column 4, column 5, and I'm going to focus in on, for first device, on column 4. This is the third row, I believe, or actually the second row, sorry. Carbons, this is the second row, boron, carbon, nitrogen, carbon. Its crystalline form is diamond. It's a very light molecule, and it has a very wide band gap. Silicon is heavier. It has a lower band gap, a smaller band gap. Germanium is heavier yet, and it has an even smaller band gap. So as the atoms get smaller as we go down from this row to this row to this row, the atoms get larger, the band gaps get smaller, and the intrinsic concentration gets larger. The larger the atom, the looser the electrons are bound, and the easier it is thermally to kick an electron from the valence band into the conduction band. So the carbon has an intrinsic concentration. Again, this is not doped. This is thermally generated. It's kicking by impact an electron out of the valence band into the conduction band. So diamond, with its very high band gap of 5.5 eV, has an intrinsic concentration of less than 10 to the minus 20th per cubic centimeter. Silicon 10 to the 10th, much, much bigger, and germanium bigger yet at 10 to the 13th per cubic centimeter. So this is what a silicon, germanium, silicon transistor would look like. Could be PNP, it could be NPN, it doesn't matter. We have a smaller band gap in the base, and somehow that is going to cause somewhat inhibited injection from the base into the emitter as compared to injection from the emitter into the base. We can see that by looking at the base efficiency. This is equation 1542. It's derived, I think, reasonably well in the text. This has to be derived from first principles. It's not something we just write down very, very easily. It's a unitless ratio, so everything that we have in the numerator, we have the same thing in the denominator as far as units go, but different values. These are the diffusion constants. These are the dopings in the base, dopings in the emitter. So the doping in the base is much less than the doping in the emitter. This is 10 to the 19th in the emitter, 10 to the 17th. So this is where we get our advantage in the normal device. But here we have a difference. We have a new term here, the intrinsic concentration in the emitter over the intrinsic concentration in the base. And for the emitter, which is silicon, the intrinsic concentration is 10 to the 10th. In the base, it's 10 to the 13th. So we get 10 to the minus 6. And no matter what these other terms here is, put in 10 to the minus 6, this whole thing is essentially 0, and the gamma becomes essentially 1, and that means that the beta becomes very high indeed. Unfortunately, things are not quite that simple, and the reason is that, as we said before, these atoms get larger and larger, and it's very difficult to deposit a crystalline structure of germanium on silicon because the atoms are so much larger, we don't get a good lattice match. So what we do is we form an alloy of silicon and germanium, which is called, oddly enough, silicon germanium, which is in the middle, more or less, between silicon germanium in its size and also in its band gap. So instead of being 0.67, this could be 0.75 or something like that. But we still get a significant advantage, and we get a good crystalline structure in the base. So the square of the ratios of the intrinsic concentration is not 10 to the minus 6, but it's about 1,000, which gives 10, instead of 10 to the 13th, it's 10 to the 12th, and we get 10 to the minus 4 here instead of 10 to the minus 6, which is still pretty darn good. Okay, so if we look at these two devices, this is the emitter and the base, we see that the dopings are the same, so that the majority densities are the same, 10 to the 19th in the emitter, 10 to the 17th in the base, whether it's silicon or silicon germanium. However, the minority the minority densities are going to be different. And we can see that by finding the minority densities, or the minority carrier concentrations. For example, in the base, these would be minority holes in the N-type base, and that's just equal to the intrinsic. This is law of mass action. This, of course, is just what we've been doing all this time. This is for a N-type silicon base, and we find 10 to the third per cubic centimeter. Of course, that's something we've seen time and time again. And for minority electrons in the emitter, we have 10 per cubic centimeter. So if we put a 10 to the 10th boost, each of these is boosted. This guy goes to 10 to the 13th. This guy goes to 10 to the 11th. Again, we've seen that time and time again. And the ratio will determine the beta. It's the ratios of the intrinsic or of the doping, and that is equal to about 100. Okay, so now we're going to increase not the doping but the intrinsic carrier concentration in the base by making the base a different material with a smaller band gap, specifically not germanium but an alloy of silicon and germanium called silicon germanium, and we're going to increase that by a factor of 100. So if we increase it by a factor of 100, then instead of having up here, where is it someplace, 10 to the 20th, we have, or 10 to the 10th, we have now 10 to the 12th. 10 to the 12th squared is 10 to the 24th. So now we have a new minority hole concentration in the emitter, not of 10 to the 3rd, but of 10 to the 7th, 10 to the 4th higher. And is the whole ball game right there. So now if we go to the non-equilibrium carrier concentration, boosted by 10 to the 10th, same boost, 0.6 volts, we have now 10 to the 17th. It was 10 to the 13th, and now it is 10 to the 17th. And then the beta becomes the ratio of the doping multiplied by this intrinsic carrier concentration factor, which is 10 to the 24th divided by 10 to the 20th, and it is 10 to the 6th. It was 10 squared. We have now upped it to 10, from 10 squared to a million, from 100 to a million. That is an incredibly dramatic increase. And so the silicon germanium Hbt is really a fabulously attractive device. They are relatively straightforward to understand. They are relatively challenging to fabricate. There's another kind of Hbt, and that's called the Gallium Arsenide Hbt. So let's go back, way back here to our periodic table. Gallium Arsenide 3,5, that is a semiconductor. What we're going to do now is make the different material, not in the base, which we did in the silicon germanium device, but rather in the emitter. So if we replace a little bit of the gallium, partially of the gallium, maybe 30%, 40%, 50%, depending on the kind of device we want to make, replace the gallium or part of it with aluminum. Aluminum is higher up in the periodic table. It therefore has it's lighter, and it has a higher band gap than gallium. Gallium has a band gap, or I should say gallium arsenide has a band gap of about 1.45. If you replace some of the gallium with aluminum in the emitter, not in the base, in the emitter we're going to get a wider band gap. 1.5, 1.6, something like that, but it's the same structure. Large band gap in the emitter, smaller band gap in the base, and we can do exactly the same thing and have a rather enhanced performance by replacing some of the gallium with aluminum. So the significant issues in the HBT are reduced bandwidth modulation, which is another name for the early effect, because the base width doesn't need to be nearly as thin as in the classical BJT, and because the base width can be made a little bit wider, then we don't have to worry about this thing called punch through. Punch through is when we have a reverse bias on the base collector junction, which is so big that the depletion region in the base extends right over to the depletion region in the emitter base junction. So the neutral base essentially disappears. So because we can make the base a little bit wider in a HBT, we don't have to worry about that. And we get a dramatically increased beta even if we reduce the doping density to be less than 100. So those are significant advantages to the HBT. Okay, so finally we'll end with a video clip which I present without explanation. It doesn't need any explanation. Giving is the best form of communication. We'll see you next time when we start on the metal oxide semiconductor structure.
ออกมานี่เลยนะไอ้ขี้ขโมยไหนดูสิเอาอะไรไปออกมานี่ไปทำอะไรเนี่ยฮะถามว่าเอาไปทำอะไรเอาไปให้แม่
เจ๊แป๊บนึงแม่ป่วยเหรอ
อย่าทำอย่างนี้อีกนะ
หมวยเกาเหลาจ๋อนั่งเลยครับนั่งเลยป๊าจัดไปอ้าวสั่งมาเร็วต่ออะไร